In this video, I'm going to demonstrate a few of the concepts that you'll use for one of the assignments involving the FAT file system. So the first thing I'd like to do is I'd like to create a floppy. And a floppy is 1.44 megabytes, and the reason I do this is that it's the simplest and one of the smallest images that you can create, and something that you might run into, not very often, but you might. And so the way to do this, and this is not something you do for your assignment, but I'm just showing you how I would go about creating an image. And I could do this with any size image that I wanted. So we're going to use DD. The input file is going to be dev0, and the output file we're going to call floppy.dd. Now the traditional standard block size is 512, but I'm going to make this block size 1024 and a count of 1440. And you see there the 1474560 bytes. That is a floppy disk. And right now it's just zeros, and if we want to look at that, we can. But it's the exact same size as a floppy image. In order to make a file system on it, we'll do vfat and make file system.vfat and then floppy.dd, and we'll arrow up and go back and look at that. And now look, it's got the master boot record for a floppy. If we go down to offset 200, we can see the FFFS there, and that means that this is a floppy. Notice the 55AA right there, that's always the end of the master boot record. Now, the end of a master boot record will always look like that. Where a floppy starts, where a FAT starts rather, will depend upon the size of the disk. So there's nothing on there, but what we'd like to do is we would like to mount that so we can add some files to it. Again, this is just how I would set up your assignment, but it kind of shows you what I'm doing so you'll know what to expect when you see an assignment like this. So we're going to copy some files from this directory, and we see we've got 3 there. Let's go back and look at those. They're fairly small, but we're only going to copy a couple of those files, and then we're going to delete a file. And actually, if you run file against those, something that you saw in Linux and also that you're going to use in the forensics class, is looking to see if there's a mismatched file type. Notice that file 1 says it's got an extension of JPEG. Down here it says it's a JPEG. This ping extension is a ping extension. The Word document is a Word document, but notice that this GIF here is actually a PDF document. How do we know that? Well, we can go in and look at the header for that, and we'll see that it says PDF. And also it says so right here. Notice that the file 5.txt is an ASCII text document. So let's copy a couple of those files. Let's copy the JPEG and the ping over. So we want to mount that, -t -t auto and o loop and floppy.dd, and we will mount that on mount. You can type mount to see that it's mounted down here at the bottom. And then let's go into this. You see there's nothing there. So we want to copy the .jpeg file here and the .ping file here, and they're there. Let's go ahead and let's delete run that with sudo because I mounted this as root. So I deleted the ping file. And is it gone? Yes. So now let's get out of this, sudo, and we want to umount it. Mount. Type mount to see if it's mounted. No, it's no longer mounted. And now we can look at this with XXD. So floppy.dd, pipe that to less. Let's go back, excuse me, hit Q to get out. Let's do file floppy.dd. Notice it says it's a DOS floppy, 1440K. So we created the right type of file. Arrow back up. Let's take a look at this. And here we see the first offsets. So the first few FFFs is saying where this starts. And notice that after you watch the FAT video, you know what this means, is that this is just a linked list, and this tells you what clusters are allocated to this first file. Do we know which file it is? Well, we will once we get to the root directory, but right now, let's just look at the linked list. So the starting cluster, this is actually going to always be the second cluster, because the starting cluster will be listed in the root directory. So the starting cluster is a logical 3, not a physical 3, but a logical 3. Well, why is that? Because the funky way that Microsoft set up the FAT file system is so that everything that's in the reserve sections or the system sections of the image, which includes the master boot record that we saw, the 2 FATs, and the root directory, are all thrown into something called clusters 1 and 2. Which, whether it makes sense or not, you just got to know that. So the first logical cluster starting is going to be 4. So this file starts out with starting at logical cluster 3, and then the next cluster is 4, and the next cluster is 5, and then 6, then 7, then 8. Well, you say, well, these numbers don't make any sense, but these need to be byte swapped, as we'll see. And if we byte swap these, and I'll show you how to do this a little later, and actually how to teach yourself how to do it, you see that this actually becomes a 004, 005, 006, 007, 008, and 9. Notice this is in hex, because then it starts with A, B, C, and so on. So recall that we deleted that ping file, so everything you see in here for the FAT, all the way to the end here, notice that these FFs, this FFFF here, if we byte swap that, that means that that's the last cluster of the file, is that there's no cluster entries, or FAT entries rather, for that deleted file. If we scroll down to the second FAT, which starts at 1400, you see right here, you see the exact same information. So the second FAT just serves for redundant purposes in case something happens to the first FAT. So we know from the FAT video that the root directory for a floppy starts at 2600. So we search for 2600. And so here are the root directory entries. And recall that for a VFAT file system, which this is, you have a short file name and a long file name entry. So notice here for file1.jpg, that's the short name entry. Above that is the long name entry. Again, this is in ASCII, 8-bit ASCII, the name. Up here you see that f.i.l. So this is going to be in Unicode. 16-bit, and that's why it takes up 2 spaces. See? F. I. And so on. So let's look at this entry here at 2620. And you'll notice that the name takes up, this is an 8.3 here. And so this is going to be the name. It also has information on the type, whether it's a regular file or whether it's a directory. It also has information on the modified access and created times in here. That's encoded. And so when you start here, the 0300, If we byte swap that, that becomes 0003, which means it starts at the third cluster. Start over. So we're at 2600, and recall from the FAT video that for VFAT you have a short file name and a long file name. The short file name is 8.3 characters, so here notice file1.jpg, and above that, and that's an ASCII, so each 8 bits represents a letter. Up here, you have the long file name, which can be up to 256 characters. And because of that, we need to have 2 characters to represent each letter. So F dot I dot L dot is in Unicode, and it's 16 bits. If we go down here to the file we deleted, notice that we have an E5 represented here and here, once for the short name, E5 for the long file name. And if you look at the characters representing the numbers, so the ILE1, they're the same here as they are down here because it's the same characters. And so you have the characters here for the file name, you have the extension, you also have characters for the type of file. The 2.0 here means that it's a regular file. You also have encoded in here the modified, access, and created times. And, sorry, let's jump back up here to file 1. If we byte swap this, we see 0300. It would be 0003, which means it starts at the third logical cluster. Just bear with me, that's the truth. If we look down here, we see that we're going to need to byte swap this, and we'll see how to do this shortly using a calculator and actually learning how to do this. And so this is the starting logical cluster unbyte swapped, and this is the file size unbyte swapped. So I'm sure you're confused now. How do you byte swap? So let's get out of here. Let's go back in. Oh, by the way, the reason I had to go back in and recreate this file is because the starting cluster and the size of the file, the .ping file, was not showing up in this original one I created, and that's because the operating system doesn't always write out the information it needs immediately. And so when I went in and originally created those files, copied them over, and deleted the file system hadn't written out the information. That's why I had to go back in, recreate this, and type sync, which means write out everything now to the file system. And so that's why it was showing up. I know this is complicated, but this is complicated stuff, and that's why people who are in forensics make a lot of money. Okay, let's open a calculator. And we're going to view the programmer's calculator. You put this off to the side. One of the things we need to do is to look at how to find the file size of that deleted file. Because if we go back, and let's go back and mount this. Sudo mount all we have is the file size for file1.jpg, right? So why don't you get a paper and pencil and write down that file size. That file size is 13883, and let's go back in and, whoops, get out of this, and let's go back in and look at 2.dd less. What we need to do is look at this file size right here that's in hex. Let's see, whoops, where's file 1? Let's go up a little bit. File 1. So here's a file size right here. And so that file size, let's put this in decimal. 138.835. That's the file size. If we want that in hex, that's going to be the file size right there, 21E53. Okay, 21E53. Look up here. 21E53. 21E53. Does that tell you how you might go about byte swapping here? If this is 21E53, then this down here becomes 21E53. So notice that there's a 2 right here, so let's write down that 2. And then it went over here to the third character, and this right here, 2, 1. So this will be 2, 5, right? So 21E, so 253. 21E53. This will be 2538F. 2538F. Does that look right? Let's clear this. So 2538F or in hexadecimal. 2538F in hexadecimal is 152463. 152463. Now you've already seen the size of this file, right? Do you remember? One 152,463. You actually saw this on a previous screen. Oh my gosh, what have we just done? Well, we've done byte swapping. And I just taught you how to do it through an example. You know, no one ever told me or showed me how to do this. I had to figure this out myself, and that's how I did it. It's by experimenting. Luckily, you've got a professor here to show you how to do it. But see, that's the same file size. Okay, the other thing we need is the, is it still mounted? No, we don't need it mounted. We need it, need to go back and look at it, XXD 2600. Notice the 0300. This should be 0003. So what does this become? What does that become? 1. It becomes 0113, right? If this is 0003, 0113. So it starts at the 113th logical cluster. So now what do we need to do? Oh, by the way, oops, let's go back in here. Something else. I asked you for the offsets, right? Okay, so the offset for, there's a JPEG and there's a PNG, right? So how do we find those? Well, we could look at the third logical cluster, right? Or another thing we could do is we could search for the signatures in the files. recall that JPEG uses the JFIF, and ASCII, or if you want to search for the hex, is FFD8 FFE0. So you can search for there. And there's the JFIF. Notice that it starts at offset 4400. Well, what about ping? What's the offset for that? Let's search for ping. We see it starts at 26400. So those are the offsets for the file. Okay, so getting the offsets are easy, right? You've got the offsets, but now we want to recover that deleted file and we want to hash it. Do we need to recover the JPEG? Well, we could, but it's all we have to do is copy it off, right? That's all we'd have to do because it's not deleted. So we want to recover that deleted file. And so how do we do that? Well, so we saw where the first file started at 4400. So how did we get there knowing that the logical cluster was 3, and how does that translate to physical cluster, and so on? Well, as it turns out, there are 31 512 byte reserved clusters for the reserved system area. So if we start out with hex and we start at the third cluster, in decimal that's 3. If we add the 31 physical clusters in the reserved area to that, we get the 34th logical cluster. So that's where that starts. If we go back and then we multiply by 512, the size of the cluster is 17408. And then if we go and we change that to hexed, it equals to 4400. So we kind of cheated for the ping file because we just searched for the ping header. But we already know that based on our byte swapping, that the logical cluster start for the ping file is in hex 113, right? Okay. If we change that to decimal, we get 275. If we add those 31 reserved clusters for the reserved area, we get 306. If we then multiply that by the cluster size, we get 156672. If we then go back and change that to hexadecimal, we get 26400, which is what we see here. So now we can use dd to recover that file. So sudo dd input file equals floppy2.dd. The output file, let's call that recover.ping. And we're going to want to skip to the start of the file, which is 156672 for a count of 152463. Now, is that everything we need? Here's the issue. The default block size is 512. So this will take out, if we included this, the standard block size, the default, it would take out 15667. It would skip here, but the count, each of these numbers, the 156 and the 152, will be multiplied by 512. We want to skip exactly to 156672 and take exactly 152463 bytes, which means we have to have a block size equal to 1. Okay, so that took out 152463 bytes. We can then run MD5 sum on both the recovered ping as well as the ping file here, and they match. And so when you're using one of those commercial tools and it goes in and it recovers the file, that's exactly what it does. Or actually, that's one way it does it. There's another way too, and we'll talk about that later. But that's how a file is recovered. And so what did you learn here? Well, you learned something about offsets. You know where the FAT1 starts on a floppy, where the FAT2 starts on a floppy, where the root directory starts. You know the logical cluster where the files start. You know the physical cluster where the files start. You learned something about headers and searching for files by header. You learned how to byte swap. And I suggest if you didn't get this the first time, run back through it, and you can do exactly what I did to create this floppy and create files of your own and byte swap and learn it that way. That's why I showed you how to do this. This is the way I taught myself. No one taught me how to do this. I taught myself how to do this. You see how easy it was to do. You just follow the little formula. And then we recovered a file, a deleted file, and then we verified it. Cool stuff.